Hi everyone, so it's Friday the 16th February, the end of week 6. This is the wrap for week 6. So I'm just going to give you a little bit of a overview of the key points from this week, very briefly. And then I'm going to cover some of the things that came up in the practical, some tips if you like. And one of the examples was about misdiagnosis. I'll just cover the logic behind working out the probabilities there for the independent study. And then I'm going to point out some of the key features of a good script, because for the assessment in this module, when you write up your experiment in the summer term, you'll have to submit a script that goes with it, from which you should be able to, or I should be able to reproduce your figures and analysis in your report. And your script should be nicely formatted. Okay, so this week we're all about normal distributions, calculating summary statistics, probabilities, and confidence intervals. So the key points for normal distributions are that they're really common. So many things that you might measure would follow a normal distribution. And because of that, then we can use normal distributions to calculate our probabilities with which things might occur. And remember, the probability with which events might occur is key in deciding whether or not we think what we see is likely or not likely in hypothesis testing. So there's some properties of normal distributions which are make it possible for us to use them for calculations of probability. And that is that we'd expect about 68% of the values to lie between -1 standard deviation and +1 standard deviation. And this is true no matter what your standard deviation is. So whether the standard deviation is 1 or whether the standard deviation is 1,000,000, you still expect about that many values to lie between +1 and -1 standard deviation. And to capture 95% of the values, then you want to be between -1.96 and +1.96 standard deviations. Okay, so these properties are key in calculating confidence intervals, in which we're doing a multiplier of 1.96 standard deviations from the mean for large samples, or something very similar, a t-value, which is also a value quite like 1.96 for smaller samples. I'm not going to go into that in too much more detail because it's already recorded on Echo. But what I will do is just draw your attention to just a couple of things in the practical. So, one thing I want to draw your attention to is this habit that I have of creating variables to give to put numbers in. So this is considered good practice in all sorts of coding and scripting. And the reason we do this, so why I've done m is 100 and sd is 15 here, and then put the m and the sd inside my function here, instead of putting 100 and 15 straight in that function. The reason I've done that is because then I can write my whole code that I might be doing using the words m and sd, and if I decide to calculate things for different numbers, then I've only got one set of values to change. I don't have to go through my code all the way along and update all the numbers. So that's one reason, is the updating makes it much easier. And then the other reason is that it often makes the code much easier to follow. So most people might be able to guess that this is the mean and the standard deviation, just because of their names. Whereas if it's numbers, it's harder to tell, because it's not described in terms of the problem, what the values might be. So that's one thing. And something else I wanted to show you was where I've used these brackets here. So this use of brackets is not needed to get the code to run. So all I've got here is a variable which I've got LCL, which just means lower confidence limit. It could be any name. And then I've got a calculation here. Now normally, if I just send that command on its own to the R command line, then it's going to carry out that assignment. So it'll put the value of this expression inside LCL, but it won't print it out. If I put brackets around it, it will both do the assignment and print it out. So that's obviously quite useful when you're working through things, if you want to both save the result and see what the answer to the result is. So it's, if you like, it's shorthand for doing the calculation and then typing LCL to output it. So now let's have a look at this probability of misdiagnosis. So the key to understanding this one is to, here we are, is to realise that you've got some people who are going to have, some healthy people who are going to have very high levels of TSH. So healthy people have a thyroid stimulating hormone level of between, with a mean of 3 and a standard deviation of 2.8. So I'm just going to use paint here to help me. So, excuse my drawing. Here we have a normal distribution, which is the distribution of thyroid stimulating hormone. It has a mean of 3 and a standard deviation of 2.8. Across like this. And so these are healthy people. H for healthy. So there are some people here, 6 is going to be about here, there are some people here who are healthy but have a value above 6. So because these people might more normally be typical of somebody with hyperthyroidism, that is, they're unusual for healthy individuals, then these are going to be treated as having hyperthyroidism. So the probability of being misdiagnosed is just simply the probability of getting a value of 6 or more from a distribution of with a mean of 3 and a standard deviation of 2.8. So we can calculate that just as we did for the previous examples in the practical. Okay, so then finally, I just want to talk to you about what makes a good script. So we have a script example in each practical, or most of the practicals, and the idea is to help you develop good practice in coding. So one of the things I already talked about was that setting up variables. So here we have that down here. I've got this setting up values into variables rather than using hard coding of numbers throughout the script. So other good features are we've got a section at the beginning which gives an overview of what the whole script is about. So you don't have to give your scripts incredibly long, meaningful names. You can do a description of what the analysis does, maybe what the data set are, and so on, in the top block of comment. And then I have other comments all the way through, which are also formatted for different types of activity in the script. So when you'll start to do data analysis, you might have one for setup, one for data import, one for tidying up your data, one for calculating summary statistics of your data, one for analysing it, and maybe one for doing plots. So in this case it's a bit different because it's not really a data analysis exercise in this practical. So you can see I've both got comments which are overview of a section, explain what the section does, and also about what the data are, what the values are, and what I'm trying to do in that section. And I've also got some comments before a piece of code, and where it's convenient, I've also got them alongside the code, because I think this makes it just easier to understand. And you can see that I've used space here just to lay out my code. So the only reason I've got extra space here is to line those comments up, because it just makes it a little bit easier to read. So the goal is, with scripting, is that your script should be nice and easy to read, so somebody else, or future you, can understand what you did and why, and don't find it painful to read. So other good practice to do with space is that we always put spaces after commas in code. We always put spaces around operators. So you can see operators are things like the assignment, the equals, plus signs, minus signs, greater than signs, and so on. Always put spaces around either side of them. Have spaces and spread your code out on multiple lines with indentation so that the code is easy to follow. Try and keep it, your code blocks not too long. and just lay it out tidily and neatly so that people can understand what you did and why. Okay. So that's all I'm going to say for this week. I'll see you next week when we'll be doing t-tests and they're non-parametric equivalents. So we've got 2 lectures, one on 1 sample test and one on 2 sample tests. Have a nice weekend.